have the following matrix A, right? We have a matrix A.
Okay.
And it's going to be 1, 2, 3, 4, 5, 6. And you'll just have to go ahead and write A transpose. So good luck and best of luck.
So this is 2 by 3. So the A transpose would be. So can I write it so I don't have to block it?
Yeah.
So this column will become the rows. This column will become the rows. And this column will become the rows. And this 2 by 3 matrix becomes a 3 by 2.
Yes. That's exactly what the transpose is. So we're going to be needing the definition of the transpose during our actual lesson. So that's why I just checked to see if everyone remembered what the transpose was. Okay, so in today's lesson we're going to be asking, what does a subspace mean? What is a subspace? So
If you have W,
yeah.
which is U.
Okay, let me write it down. If you have W,
No, I think if you have a U and V, and you have some property and V has some properties, so U plus V would be all the properties in U and all the properties in V.
and V. Right.
Is that right?
Yeah, but that's a little bit complicated. So I'm going to simplify the idea of subspace using the idea of water. Who's familiar with water?
Me.
Can we? Okay. Other two people in the room? No. Not familiar with water? Okay. Water usually comes in a bottle, right? We all agree on this?
Yes.
I thought it usually comes in the form of an ocean or lake.
No, that's fake, my friend. Don't fall for that bogus.
What?
Now,
That's misconception.
this water, we can
It comes
say
from filtered ocean water.
we can say that this water is a subspace of this bottle.
It's literally
Right?
made out of condensed water.
right.
Gas.
So this water is a subspace of this bottle, right? If I drink away some of the water, will the remaining water still remain in the bottle?
Yes.
Yes.
No,
Genius.
is what you might think. But actually, let me try and do it. So I'm going to go ahead and try to drink some of the water. Let's see if the remainder of the water remains in the bottle.
Oh no, it's gonna go to your belly.
Okay, let's see.
You drink all of it.
It is going to your belly. And some of it still live there for me.
But the remaining lives there for whoever comes next, right? The live audience seems to think that I'm lying, but there you go, just to prove it. So what does that prove?
That proves nothing.
No, that proves that if I make the size of the water smaller, the water still stays in the same space, right? What do we call that? We say the following. Do we have an answer? No. All right. So we say the following. So instead of this
What if
complicated
we made
thing,
it small enough that it would leak through a tiny hole?
so this is our bottle, right? This is our bottle and this is our water. I'll call my bottle B and I'll call my water W. Who's comfortable with those letters?
Me.
Me. Okay. And of course we can say my water.
As long as you don't use the Greek or Hindi.
I can't promise I won't do that. So we know that the water is part of the bottle, right? And I just showed you that if I decrease the size of my water, it stays in the bottle. So what does that mean? It means that my water is closed under scalar multiplication. Okay? Closed under scalar multiplication. What does that mean? What does that mean?
So 2 plus 3, 2 is a real number, 3 is a real number, 5 is also a real number.
But scalar multiplication actually doesn't have to do with adding.
Oh no, well,
It has to
okay.
do with
So 2
dividing.
times 3 is 6. So 2 is a real, 3 is a
Okay.
real, and 6 is a real.
Well, let's say we have this amount of water,
Okay.
right? If I
Are we discussing arithmetic or something?
if I take half of that water, it's gonna become smaller, right? But it's gonna
This is
stay.
basic algebra.
But it's gonna stay in the bottle, right?
Yeah.
Right. So that's what it means for my vector subspace to be closed under multiplication. Even if I multiply it by some scalar, it stays in the bottle. I can make the water infinitesimally small.
Right.
It will stay in the bottle. I can add more water. It will stay in the bottle. Now, speaking of adding, what do vector subspaces also have to be closed under?
Addition.
Addition, 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 addition. Okay, so what does that mean? That means if I have my water bottle and then I pour in some more water, all the water is going to stay in the bottle, right? So that means, here. So let's see how far I can take this analogy. So here's my bottle, here's my water, and I'm going to pour in some extra water, right? Through maybe a faucet or some other kind of hose. Seems like I need this water right now.
Stay hydrated, everybody.
Stay dehydrated, and you'll face the consequences. Okay, so what do we have? We have the bottle and we have the water, and I just said if I add more water droplets to my bottle, all the water is going to stay in the bottle, right? So that means my vector subspace is closed under addition. Okay. Who feels comfortable with that? Who feels comfortable with that? Anyone feel comfortable? Okay. I, for one, feel very uncomfortable with this analogy. But if it works for the viewers, it works for me.
Blech.
Okay, let's move on. Now, I want to formally define what a vector subspace is, not using water and bottles, but using symbols that will hopefully confuse you.
Hopefully confuse us? Not the
So-
point of this class is to learn.
So let's
Not to be confused.
let's first return to the definition of a vector subspace. We know that a vector subspace is closed under two things. Number one, a vector subspace is closed under what two things? Number one, what? It's closed under what and what?
Addition and multiplication.
Right. It's closed under addition and scalar multiplication. Not vector multiplication, scalar multiplication. Who's comfortable with that? Who's comfortable with that?
Yeah.
I'm comfortable with it too. Now, I will try my best to make you as uncomfortable as possible
What?
by introducing as much Greek notation as humanly possible. Okay? Let's begin with
What?
a circle
Okay.
and a smaller circle.
That's fine.
Who's comfortable with that?
Me.
Two concentric circles, right? We'll call this W. Let's call this B for bottle, and let's call this W for water, right? So far, so good. This is just like the water bottle analogy, right? Okay, so I'm going to say a few things, okay? Let's say in this set W, I have two vectors, W1, W2. So far, so good? Okay. Now I can write in mathematical notation that both of these vectors, W1, W2, are elements of W. Who's comfortable with that? Who's comfortable?
Me.
That's good. Okay. And since W is a subset of B, I can just go ahead and say those two vectors are a subset of B. Right? Everyone feel good so far? Okay. Now,
Holy.
if
Yeah.
W is a vector subspace, if W is a vector subspace, then, okay, this is like, if you're on a mountain, this is the top of the mountain. So this is very important right here. W is a vector subspace, then what? Then what? What do we know to be true? What have we just done over the last 5 minutes? Qualitatively. We want to formalize this. Number one, what's true? A vector subspace is closed under?
Addition and scalar multiplication.
Okay, so let's do addition first. How can we show that W is closed under addition? It's easy. I can say the sum of these two vectors is still in this set B.
That's it.
That's it. Just like if I add more, oh, you can see my water bottle just fills up. But all the water is still in the bottle. Same thing. If I add more water, if I add more vectors, it's going to stay in the space, right? So we've satisfied that condition. What's our next condition that a vector subspace must satisfy?
It closes in scalar multiplication.
Close under scalar multiplication. Okay. So scalar multiplication. What letter do you want?
X.
No, any letter. One letter.
X.
Okay. So. Okay, there you go. X, and let's say X represents a scalar. So it's a set of real numbers, right? X is an element of the set of real numbers. So for example, X could be 1, X could be 2, X could be 3, right? It's just scalars, right? So, if W is a vector subspace, then what? What can I say with X?
Vx is also in the real number.
Very close, but we're dealing with this vector subspace W.
So Wx is still in the real number.
Right. In not the real numbers, X is in the real numbers because it's a scalar. This is going to be in the overall space, the overall vector space. X, W is an element of it. Okay? So these two things are all you need to define a vector subspace or even a vector space. Okay? Who's comfortable with that? That doesn't seem too crazy, right? Not too crazy, but we've only touched the tip of the iceberg. Okay? So now that you've understood what a vector subspace is, let me take you to the most important idea in all of linear algebra. In all of your linear algebra history, you will never encounter an idea more important than this. What am I talking about? Who knows? Who knows? Anybody want to guess?
Subspace.
Subspace, yes, yes. What type of subspace? Anyone want to wager a guess? Who wants to wager a guess?
What does wager mean?
Okay. Now, what was I about to say? Well, I was about to discuss the 4 fundamental subspaces of linear algebra. This is, who's heard of the fundamental theorem of algebra? Okay, okay. One student obviously uses algebra but hasn't heard of it. Okay. Who's heard of the fundamental theorem of calculus? Okay, okay. Now you're about to hear about the fundamental theorem of linear algebra. Who's excited? Who's excited? Okay. All I see is depressed faces. But that's okay. So, the fundamental theorem of algebra has a special name. It's called the 4 fundamental. Who wants to fill in the blanks? The 4 fundamental what?
Space.
Subspace, yeah. Subspace. Subspaces. Okay? It's almost like the Holy Trinity, but if there was a 4th one. Okay? And yeah, that was a bad analogy. Okay. So 4 fundamental subspaces. What do I mean by that? Well, let's start with a matrix. Okay? We had a matrix in the do now when I randomly asked you to find the transpose, but hopefully now you will see the benefits of me asking you that question. So let's start with a matrix. A equals 1, 2, 3, 4, 5, 6. Who's okay with that matrix? Who's okay with that?
Yes, I'm good with this.
I like this matrix. You know why I like this matrix?
It's 1, 2, 3, 4.
That's
5,
correct.
6.
That's right. That's why I like this matrix. Okay, there are 4 fundamental subspaces of linear algebra. Number 1, and number 2, number 3, number 4. First things first, we begin with the row space. The row space. Then we have the null space. Then we have the column space. And finally we have the left null space. Okay, so these are the 4 fundamental subspaces of linear algebra. Okay, now let me make this clear. I don't know what any of these words mean. Okay, so why don't we begin with the first 2, the row space and the null space. So these words might look very weird, very scary, but we're going to break them down step by step. First of all, row space. Let's start with the row space. Who's comfortable with that idea? Who wants to start with the row space? Okay, me. Thankfully, I'm the only voter. The row space. Okay, so can somebody tell me the rows of this matrix? What is it? What are the rows of this matrix? Do I have any volunteers? Ah, yes, Alex. Yes, thank you for volunteering. What are the rows of this matrix? Ah, yes, Alex. Yes, thank you for volunteering. What are the rows of this matrix? Okay, hopefully that was enough time to answer the question. Okay, who's frustrated right now? Give me a hands up if you're frustrated. That's right. Thank you if you're frustrated. All right, Mr. Frustrated right here. Tell me, what are the rows of this matrix? I'm going to leave that as a question for the audience. So go ahead, try to answer that for a few seconds. Okay, who's ready? Who's ready for this?
Me.
Who's ready for this?
Me.
I'm ready for it. Okay, so can you tell me the row? Okay, we're gonna start with the row space, the first fundamental subspace of linear algebra. So what are the rows of this matrix? The rows of this matrix. Rows of this matrix? Huh? The rows of this matrix.
Oh, 2 rows.
Okay. What are they?
1, 2, 3.
1, 2, 3,
4, 5, 6.
4, 5, 6. Okay, those look like very nice numbers to me. Okay. Now, what if I graph this out? Let's see what happens, right? So let me graph it out. What's gonna happen? This vector, both of these vectors exist in what dimension? R what?
3D.
Okay, so R3, right? So they are both elements of R3. So I'm going to draw the 3-dimensional coordinate plane. And I'm going to draw these vectors. Maybe this is 1, 2, 3. Maybe this is 4, 5, 6. Right? Now, I want the audience to tell me 2 words. Who's ready for this? 2 words that describe these 2 vectors. La. I'm literally saying the word. Linearly independent. They're linearly independent. Okay, now we have a shipment. Now these 2 vectors are linearly independent. Right? Who agrees with that? Do you agree with that, Alex?
Yes, of course.
They're
They're not going to touch each other. No matter what is your.
Okay.
No matter what is your C is being
So
constant.
tell me their span.
Span is R1. R2.
R2 because they don't touch each other. Yeah, so they're gonna make a plane, right? Okay.
If
so,
they all touch each other, then it would be R1.
Right. So how can I write the row space? Well, I can write R for row, and I can write the matrix A, right? And what is the span of my row space?
R2.
R2. And we have transcended to the higher dimension.
Drum roll.
But we're not done. we're just getting started. Okay, that was the row space. That was the row space, right? But I haven't proven that the row space is a vector subspace. You just took my word for it. How can we prove that the row space is a vector subspace? What are the requirements of being a vector subspace? Who remembers this? Does anyone remember the requirements for being a vector subspace? 10 minutes ago? Literally 10 minutes ago? Well, it has to be closed under
Addition by scalar
Right.
multiplication.
So that means V1 plus V2 have to be elements of the overall set, and then C, a scalar, times the vector still has to be an element of the overall set, right?
Drum roll.
At least we have one student who appreciates my work. Okay, so that is the definition of a vector space. Our goal is to prove that the row space is a vector subspace. How can we do that? First thing we have to demonstrate is that if I add any two vectors in my row space, I'll end up with another vector that's still in my row space. So for example,
What?
let's say I take 2 of this vector and 9 of this vector, and I add them up. Will my resulting vector still be in the row space?
Yes.
Yes, it'll still be in R2, right? Any linear combination of these two vectors will still end up in R2. Okay, let me adjust my question. Let's say I have this vector, 1, 2, 3, and I scale it up. Is it gonna stay in that same plane?
Yes.
Yes.
Drum roll.
Well, we have just, okay, that's too much. So we have just proven that the row space is a vector subspace, right? Now we have to do the same with the null space. The null space. Now, what's a null space? Who wants to wager a guess as to what the null space is? Do I have any volunteers? What is a null space? What a weird word. Who even comes up with a word like that? Mathematicians. Useless. Okay, so what is a null space? Who wants to guess what a null space is? Has anyone ever heard of a null space here?
No.
Well, I'm about to knock you viewers into null space if you don't give me a definition soon. Okay, this is sad. A null space, folks. A null space.
What is a null space?
A null space.
A space
I wouldn't
with
expect you to
nothing in
know because you haven't been looking at my lecture, my friends. Let's keep our eyeballs where they belong, which is on the whiteboard. Okay, so what is the null space, you might ask? Well, the null space is simply all the vectors that are a solution to our matrix A. V is equal to the 0 vector, okay? So let me repeat that. The null space is a vector subspace of the vectors V such that AV is equal to the 0 vector. Hopefully that makes sense. Hopefully that makes sense. Wait, let's get a raise of hands. Who makes sense?
Who makes sense?
Okay, I'm sorry. Does that make sense? That's what I meant to say. Does that make sense?
No.
Actually, it made so much sense to one viewer, he got knocked out. Okay. So now, AV is equal to 0. But how do we know that's actually a vector subspace? Well, we have to prove, using the two requirements of a vector subspace, that the null space is indeed a vector subspace. Okay? Now, how do we first and foremost denote the null space? Well, I'm going to write N for null,
Oh shoot.
and I'm going to write A.
What is
That's going to be
Alex
my
doing?
null space, okay? Let's stay focused, my friend, because unfortunately, I haven't seen any... Okay, I'm joking, my friend. I like to joke. Now, the null space of A.
Thought you were a teacher.
Okay, so our goal is to prove that the null space of A is indeed a vector subspace. And how do we do that? Well, first and foremost, we must show that the addition requirement, that the null space satisfies the addition requirement of a vector subspace. So let's go ahead and do that, okay? So, let's say, given two vectors v1 and v2 that are already elements of the null. Let's not wear headphones to shut out the teacher's voice here. We can all be civilized. Now, let's say these two vectors are elements of the null space. Will their sum also be an element of the null space? As a matter of fact, yes. Because take a look what I can do. If these two vectors are elements of the null space, what do I know? I know that if I multiply them by the matrix A, they're going to equal the 0 vector. Likewise, if I multiply A times V2 by the matrix A, I'm going to get the 0 vector. And if I add those two up and suck up A, if I factor out A, what am I going to get? I'm going to get A times V1 plus V2 is equal to the 0 vector. Wow! And we know A is a non-zero matrix. I mean, that was our whole condition at the point. I mean, I didn't explicitly say that, but it's kind of obvious that you should have a matrix that is non-zero. Otherwise, your I hat and j hat become transformed to literally the 0 vector, which is useless, basically. Okay, that means what? That means that if A is non-zero, that means the sum of v1 and v2 have to be 0. And thus, we have proven that the null space satisfies the addition requirement of a vector subspace. But we still have one more step to go, right? And what is that one more step? That one more step is to prove that the null space satisfies the scalar multiplication requirement of a vector subspace. In other words, we still have to prove that the null space. What do we have to prove? Wait a minute. Okay, we still have to prove that the null space is closed under scalar multiplication. And thus, if we prove that, we will have shown that the null space is indeed a vector subspace. After which I'll do one more additional miniature proof. Okay, so how do we do that? Well, let's say we have a vector v1, v sub 1, that's an element of my null space and of A. Okay, and my goal is to show that C times v1 is also an element of the null space. Now how can I do that? Well, I can, of course, I know that since v1 is an element of n of A, I know that A times v1 is going to give me the 0 vector. So if I go ahead and just multiply both sides by my scalar, I'm going to get C times A times v sub 1 is equal to C times the 0 vector, which is of course the 0 vector, right? So I'll have, because of the associative property, I can just factor out that A and get C times v sub 1 is equal to the 0 vector, folks. And thus I have just proven that the null space is closed under scalar multiplication. Thus, the null space has satisfied both requirements that need to be met by a vector subspace, to be a vector subspace. Okay? Now, let me give one more additional miniature proof before we close off today's lecture. And that is that every vector subspace has to map the 0 vector to the 0 vector. What do I mean? What do I mean? Well, the null space, this matrix A is a transformation such that it takes all R2 vectors, all vectors in R2, back to R2, right? Now, now I've knocked out 2 students. I only have 1 more remaining. Now, let's see if we can knock her out. Okay, so our matrix A takes any vectors in R2 back to R2. Now I'm going to show you if that satisfies the 0 vector, okay? So, let's say our matrix A is as follows, right? We're going to have A sub 11, A sub what? Rows, columns, all the way to, if this is an m by n matrix, rows by columns, I'll have one A sub 1n. And then I'll have A21, A22, A31, all the way to A sub m1. And that continues all the way to A sub mn. I did that really quickly, folks, simply because all my students are leaving. Now, let's let's just go ahead and multiply that by a 0 vector, and let's see if that outputs a 0 vector. And of course I have 0 viewers. Now let's go ahead and multiply that by the 0 vector, and it's clearly, by any matrix multiplication you do, you'll see that multiplying these two will give me the 0 vector, and thus we have proved that the null space and the row space are both vector subspaces of the overall matrix. Thank you for watching.